I thought I'd give sort of a high level overview to kick us off, and I think some of the subsequent speakers are going to show more data and science unfolding from the region. So I'll just sort of step through what we know and where we're at as a region and a little bit as a globe. Uh, I put this slide in a lot of my presentations when I'm talking about blue carbon, and I think it's a little bit less relevant for this group, but it's the sort of acknowledgement that when we're speaking about blue carbon, we are not discussing whether or not this is a substitute for cutting emissions. Like we still need to stay below key thresholds of 2 degrees of warming, for example. We have to do the conventional mitigation techniques in blue, like converting to solar, but also those scenarios now include carbon removal approaches. And the restoration, conservation, and good management of blue carbon ecosystems is one of those carbon removal approaches that also, from my perspective, is a great bet because we're also doing things like supporting fisheries, and all of the other co-benefits that those habitats provide. So there's the sort of the back context in all of this is, as always, that we do this for carbon benefits, but also all of the other things that we know they provide. So worth stating in particular with the carbon crowd, because sometimes those things get lost in the wash. But if this is a fisheries crowd, hopefully we all already know that a little bit. And then also because this is the very beginning of these presentations, it's worth a reminder that the carbon biogeochemistry in these habitats is complicated. Carbon moves vertically and laterally. You get emissions of methane, nitrous oxide, sequestration in sediment. But the sort of traditional scope of blue carbon sequestration is the fact that they have relatively high sediment accumulation rates and low decomposition, which leads to the sort of long-term millennial timescale sequestration of carbon in sediment. And that is the sort of value that was originally scoped with respect to blue carbon habitats relative to other habitats, maybe a terrestrial forest that sequesters carbon in its living biomass and holds on to that for a certain duration, but it may be ultimately remineralized faster than this old carbon stored in sediment. And if you look at some of the data we have to date, which will be highlighted in future studies, this is an adaptation from the Kaufman paper in 2020, we can see that most of the organic carbon in blue carbon ecosystems across the US West Coast is stored in sediment, which is true generally speaking globally, with the exception of mangrove forests, or in the Pacific Northwest case, tidal forests, where you do get some of that carbon stored in above ground biomass in the woody tissues. The other thing is that seaweed and kelp, which I spent some time working in, is a newer blue carbon habitat on the scene, so to speak, and that the mechanism for that differs a bit in that it's not stored in the below ground biomass and in sediment, but rather exported to the deep ocean layers to be removed from interacting with the atmosphere. So still potentially valuable, but different in the way we would quantify those carbon benefits and sort of the approaches to managing those carbon stores. So, like I said, like these habitats have been valued for a long time for many different co-benefits and ecosystem functions, and the carbon benefits are newer on the scene. And as we've sort of come to realize these benefits from a carbon or climate mitigation perspective, they've become quite prevalent in both our global climate action and our regional and local climate action. So I don't need to read through all of this, but this sort of highlights some of the history of how blue carbon has now come to be represented in climate and greenhouse gas goals, starting with the UNFCCC in the 90s. That was one of the earliest sort of efforts to document the natural carbon sink abilities of our ecosystems, followed by the Kyoto Protocol, which was one of the earlier mechanisms, the CDMs, to support carbon credits, so the monetization of this function. And then we come to the sort of Paris Climate Agreement and tracking our greenhouse gas progress goals, tracking progress for our greenhouse gas goals, which includes blue carbon habitats. And, you know, the sort of less carbon focused initiatives like the 30 by 30 initiatives the UN Decade on Restoration, Sustainable Development Goals, and all of these global actions call for us to do a really good job monitoring, tracking, restoring, managing blue carbon ecosystems. And we can see that also reflected in regional climate action. And this started long before we knew about their carbon sequestration abilities, primarily because of their fisheries value. So if you look at the history of the definition of seagrass as essential fish habitat, those protections came through the Clean Water Act and the Magnuson-Stevenson's Conservation and Management Act as a value for fisheries. And our mitigation policies are designed around that function because that is how they were originally written. We have less strict policies for seaweed habitats, in part because the drivers of loss of seaweeds and kelp are not as pointed. So it's hard to ask somebody to mitigate when the driver of loss is a marine heat wave, for example. And then, that's sort of the historically how we've managed those habitats with respect to mitigation. But now we have this sort of new era with respect to blue carbon, where we're valuing carbon functions in addition to those fisheries functions and looking for ways to manage habitats with respect to those functions. And you can see this specifically as carbon reduction targets. So I work a lot in California, and we have our climate change scoping plans that lays out scenarios to reach greenhouse gas targets. And those include blue carbon habitats. We have protection targets looking to reach 30 by 30. And there are also specific regional restoration targets. So reaching 300 acres of eelgrass in San Francisco by 2030 and 3,000 by 2038. The California Natural Resources Agency scoped new goals this year to restore 12.2 thousand acres of wetlands every year until 2045. Washington had a goal in 2011 to increase eelgrass area by 4,200 hectares by 2020. So there's lots of these sort of regional targets that have been set. So now there's some additional pressure on us as a region to do a good job restoring blue carbon habitats for the multitude of functions that they provide. So, clearly this is not the first time we've sought to manage blue carbon ecosystems effectively. We have a long history of that as a region, and some of the work that PMEP supported a couple of years ago was to pull together some of the restoration efforts that have been done on eelgrass specifically over the last decades. And that's some work I did with my colleague, Kat, and we can learn a lot from that history. We have an earliest project in the US in the 40s and on the West Coast in the 60s. And that's a pretty tremendous knowledge base we can work from. If you look, for example, at the UK, who restored earliest, despite the fact that they've lost some 90% of eelgrass there, they started their first restoration project in 2019. So we have like a big knowledge base to learn from. And I'm not going to get into all the results of that work. As Todd and Joan mentioned, there's the full report, but we do learn some interesting things from that effort. We found about 82 publicly available projects, and they're scattered along the West Coast. And you can see that these purple and blue bars are projects that were done for mitigation, and the green and yellow are projects that were done maybe by an NGO or a community group, that kind of thing. And so one thing that tells me is that we're doing a lot of restoration from the stick rather than the carrot approach, which does work, but it has its limitations. And part of that sort of, because we're doing those approaches for compliance, people often do only what they are required to do to check that compliance box, and then they walk away. And so it's hard to get the monitoring data that you want from those projects. If you want anything other than what's required, it often doesn't exist. There's some mixed results of success. So about 30 to 60% of the plots that we evaluated were no longer successful by the project end, but that margin is wide because success for whom? And or how are you defining success? And all of this comes to matter when we think about how we've changed our value of different functions over time, whether that's for a fisheries perspective or a carbon perspective or anything in between, water attenuation, shoreline stabilization. Pick your function of interest and define your success, and then evaluate whether or not you've been successful. What we hope to do with that work was evaluate success based not just on structural attributes, which is common, aerial coverage, shoot density, but also on functional success. So like, do we see the same level of biodiversity in the restored plot as you do in a natural meadow, or as you did prior to disturbance, or fisheries, or OA amelioration, or carbon stocks? But because so many of those projects were for compliance and or on a limited budget, there was almost no evaluation of functional success, only structural success. And if they did measure functional success, it was a very different, way of measuring. It was one was measuring OA and one was measuring salmon and one was so we couldn't really compare. So we could not make functional success evaluation. And that may be fine if our structural attributes sort of beget functional success, and we can make that case. And in some cases, maybe it will. Maybe having a sufficient shoot density will equal, the same level of biodiversity over time. But from a carbon function perspective, which is sort of what we're talking about today, that may not really be appropriate anymore. So if you dredge a meadow, if you're Caltrans building a bridge and you lead to the loss of a seagrass meadow, and then you transplant it over here, in another location for your mitigation, that meter of sediment below that seagrass meadow could represent some 500 years of carbon sequestration. And so if you restore elsewhere, you may get the fisheries functionality back in 5 years, but you almost certainly will not get your carbon functions back in 5 years. So sort of similarly, if you do a restoration project, regardless of mitigation, and your restoration is only successful for 2 years, you might think, gee, I failed, or 1 year even. But if you're a vulnerable life stage of an oyster or a juvenile lobster, it may matter that your seagrass is persistent for 1 year or 2 years. And so you can see how we may flex our definitions of success based on the function of interest. And in the carbon market world, we define success as 100 years of carbon sequestration. So the timelines here are very different, and something that as practitioners, we can think about when we design a restoration or management program most thoughtfully. And then also sort of zooming out to the seascape, where if your patch was only around for 2 years, but it's facilitating propagation of seeds in another place, just starting to think about those kinds of things. So restoration is expensive. We are sometimes failing. And we have all of these new goals, the 30 by 30, the greenhouse gas goals, and we're looking to scale out our restoration and conservation approaches in a pretty big way if you look at some of the lofty aspirations we have regionally. So are there ways that we can, one, improve our management to reach those goals, and two, like look for non-traditional finance mechanisms through which we could do this? And I'll touch on this a little bit here, but the carbon markets, I suppose, are or nature markets, I should say more broadly, are one of the ways that is being discussed to scale these restoration and conservation efforts into a larger arenas. Can we get more acreage? How can we finance all of this? And there's a lot that could be discussed about whether or not we should, or how we should be monetizing the ecosystem functions of all of these habitats. But if we sort of accept that they're one tool in the potential tool belt, we can look at whether or not, or how appropriate that might be. And I think there's a lot of questions and unknowns about if and when it would be appropriate to use these carrot instead of stick approaches, if you will, to incentivize the restoration and conservation of blue carbon habitats. And so I think then, how then do you know if you could benefit from a carbon market fund to support a restoration project? A question which goes hand in hand with, like, are there ways to maximize the carbon functions to leverage those funds? And if you do that, are you sacrificing other functions? Is a project that's high in carbon sequestration low in fisheries? Can we maximize multiple of those? And so, not all approach to managing a certain habitat is going to be the same. There are very different approaches, and they all come with different timelines of success depending on your function, and different potential carbon outcomes. And you can think about some of these, like I've outlined 5 here on the left, where you could just plant plants. You could do a tidal reconnection or restore the hydrology. You could do that in tandem with planting plants. So for example, one of the projects I'm working in Elkhorn Slough on, where they're doing the large scale restoration and there's new channels being dug, and then we put seagrass into those channels. So that's sort of a combination. There are some reduced subsidence projects that have huge carbon implications. So for example, in California's climate change scoping plans, one of the scenarios we've evaluated is to reduce the subsidence in the delta that has a tremendous amount of remineralization of carbon occurring as we've dropped that water table, leading to subsidence. And so changing agricultural practices and hydrology is a very different approach to restoration, if you will. Approaches using sediment management, so like beneficial use of dredge, and then of course conservation projects, which from a carbon perspective, the baseline matters profoundly. In other words, like what would have happened had you not intervened, and your carbon gain is associated with the difference between what would have happened had you not intervened and then what happened if you did. If nothing was going to happen, you're not gaining much carbon per se, but if you were going to lose that seagrass meadow, then your carbon gains are sort of inflated. And this is a product of the way we think about carbon markets. But if you're not doing it from a carbon market perspective and you're doing it simply for the other benefits, your baseline may matter less. So the application always matters. And then I don't want to get into the whole nuts and bolts of this model, but one of the things that I've been working on most recently is to try to scope out like can we ballpark what we would expect in total carbon sequestration and therefore carbon revenue potential from credits for all of these different kinds of approaches. And so I built a model based on the Virginia LTER because that was the only site globally I could find that had all of the necessary parameters. So carbon sequestration and sediment, methane emissions, all relative to a baseline, and sort of modeled what we think would happen to a restored meadow or a conserved meadow if you were applying an infill approach, so like adding sediment, which we do. I skipped that, but this figure on this page, the one with the red circle, this is a seagrass restoration project where they didn't have space to put the seagrass meadows, so they built a retainer wall, filled it with sediment, and planted the seagrass on top of it. So we have entered the space of kind of wacky restoration in some contexts already. And then sort of less exaggerated sense, we do things like thin layer placement or sand capping. So this is a very for back of the envelope calculation about how much carbon credit revenue we could get. And it's, the price of carbon is a big conversation as also. So I ran it on 2 prices, $30 and $70 a ton. And just to give you a sense of what you might expect, over 10 years, and a seagrass project could generate $20,000 to $1.5 million in carbon credits for a 100 hectare project, or $1.2 thousand or $92,000 for a 6 hectare project. And that does not include the cost to actually implement the project. So like, what does all this mean? Those track with the amount of carbon they could possibly sequester. But also if you look at how much we're doing restoration, if you talk to the practitioners in San Francisco Bay, over 13 years of ongoing restoration, they've restored about 40 hectares of seagrass. So we're not doing these 10, 20,000 hectare projects like you see in a lot of mangrove projects in the global south, for example. And so it changes the carbon math on how appropriate they would be. It doesn't mean that there's no possible opportunity for carbon credits in our region, but that it has to be, I would think critically about, are you using sediment management approaches? How big is the project? How much is it going to cost? Is it worth it to go through those processes to get credits or not? And so just sort of thinking about those kinds of things. Also, conservation is essential, and that's always been true, no matter the function. But if you can keep carbon in the ground where it would have been remineralized otherwise, you're always going to be better off. And we can see some of these scenarios that might be appropriate for carbon credits in other regions of the world. So for example, Shark Bay in Australia had a marine heat wave that led to the loss of a lot of seagrass, which then has been subsequently eroding the underlying carbon stocks. And they've lost about 60 centimeters of topsoil after following the seagrass loss. And so if you can put the seagrass back to cap that sediment in place, you may have like a strong argument for conducting a carbon project, but that's going to look very different than if you're just transplanting seagrass. And so this is the sort of thought process that goes through the carbon markets. And now we're sort of entering the new space of biodiversity and nature markets and similar sort of complexities within all of that. But they are one possible tool to support conservation and restoration, but may not always be the best and may not always cover the cost of the project, depending on any number of factors. So I'm just going to finish with a quick highlight. I think I'm roughly on time of some science gaps because I'm supposed to be doing the sort of high level. And again, the gap is tailored to the interest. So lateral fluxes are generally interesting from a carbon market perspective in particular, because you don't want to credit carbon sequestered by your project if it's coming in from somewhere else. So we have all of these rules around autochthonous and allochthonous carbon. And so that's a big focus. The mapping and monitoring has been a big focus, and that's true for tracking greenhouse gas inventories. And we're making these goals, whether that's a greenhouse gas goal or a restoration goal. And in particular for seagrass habitats, which mapping is difficult from a remote sensing perspective. If we don't know how much seagrass we have and how it's changing, and we're not tracking it, it's very difficult to say whether or not we're achieving these goals. And so we have a big sort of hurdle to overcome in order to make sure that if we're setting these goals, we can actually determine whether or not we are reaching them. And that's a mapping and monitoring question. And then the modeling to accompany this. So if we're trying to we're trying to track progress towards state greenhouse gas goals, and we want to know how all of our management is affecting our progress towards those goals, we need good models that can ingest all of that map data and have some mechanistic understanding of the biogeochemistry to then say, okay, we did X and the greenhouse gas outcome was Y. And this is how much progress we've made. And that requires a bunch of data and also good models. Developing emissions factors. So I think somebody might mention the Pacific Northwest Blue Carbon Calculator, which is basically based on emissions factors. So like, a tidal reconnection project is expected to have this greenhouse gas outcome. I'm going to do this. What do I get? And that also requires all of the carbon stock data that I think Chris will present some of. So we're really ingesting all of the science that we've been doing for the last decades to apply it now. And it just fuels the need for ongoing science. And then some other questions on alkalinity, which we don't really have time for. And then some of the things that I mentioned before on how different functions return following restoration, depending on your interest. And I think that will do it. And I will take questions.
Thank you, Melissa. I do think we have a question in the Q&A box, and I think we also have one in the chat. So, Holly, do you want to read the question that's in the Q&A?
Absolutely. And as Joan mentioned, we'll be using the Q&A function for questions. So you guys can access that down at your little toolbar. There'll be a little thing called Q&A, and you can just type your questions in there. Question from Melissa from Jacqueline Bars. What about restoration mechanisms for eelgrass that reduce threats which would result in loss or decline of beds, such as eutrophication that results in algal blooms that decrease light penetration to an eelgrass meadow? This is related to your slide mentioning that not all restoration approaches are created equally.
Okay, sorry, I was trying to find that in the chat so I could read and listen, but I think the question was...
It's in the question and answer.
Oh, I was in the chat. That's no problem. The question is about... Can you read the very beginning of that question again? The conservation is about baselines?
Yeah, I think we're asking you to just elaborate on restoration mechanisms which focus on reducing potential threats that would result in an eelgrass bed or a seagrass bed.
Yeah. So, I mean, it's always hard to answer these questions because if you're a carbon credit project, there are these very specific requirements. And some of the critiques with carbon markets have been in exactly this, which came mostly from the forestry sector, where you could do a carbon project by saying, oh, this forest was gonna be lost and I stepped in, and then I get credit for all of that. In other words, like, if you were going to lose 10,000 units of carbon and you implemented a measurement to conserve that terrestrial forest, and you do nothing other than implement that, then you get credit from all of that. And then people have critiqued the baseline. Like, well, how could you know that that forest was going to be lost? You're asked to sort of use a crystal ball to project what would have happened and then claim credits on that. And if you're in sort of shaky ground, if you can't really prove that without your conservation measure that was going to happen, and then you're just issuing credits. In other words, somebody's saying, I reduced my greenhouse gas impact or carbon footprint, and I did nothing and nothing would have happened anyways. They can look like faulty credits. And that is super important to sort of close that loophole. But that said, like, if you really would have lost that forest, or in this case, a marsh or a seagrass meadow, then the conservation measure is super, super valuable. And so, with that in mind about carbon markets, you have to be really careful. Whereas if you think about our 30 by 30 initiatives, or any of the other reasons we've always conserved these habitats, like, we should just be doing it, even if we're not trying to get carbon credits. From the less of the finance perspective and more of the biogeochemistry perspective, it depends on what would have happened. So, like, if you can prevent remineralization, which I think there was a question in the chat. In other words, just like organic carbon that gets munched up by microbes and converted back to atmospheric CO2. If you can prevent that from happening, whether that's reducing erosion through a good seascape of habitats, or transplanting seagrass on top of sediment that's eroding, like in Shark Bay, like, those approaches are going to have higher carbon benefits than sort of adding plants into a place doesn't have any ongoing sediment management in tandem, if that is helpful.
Thank you, Melissa. It looks like that also answered Fran's question in the chat for explaining what remineralization is and how that reverses carbon sequestration. Jacqueline specifies she was thinking more about restorative mechanisms of riparian buffers to minimize eutrophication downstream to eelgrass meadows. So I guess restoration of adjacent habitats that would, impact.
I mean, I think we know that, like, seascape level restoration is going to be a more productive outcome than looking at things from the individual habitats. And I think some of the most successful restoration projects have been on this, the sea landscape, whatever you want to call it, that have restored multiple habitats based on all of the, like, movement of sediment and nutrients. And that absolutely works. And the UK, where I did some work, is particularly impacted by eutrophication because of their water regulations. And they are pursuing these kinds of strategies more than we are. And they're also looking at things like nutrient credits, which, like, cue the monetization discussion, but, like, can they do a restoration project and get a nutrient credit, which ties into their water regulations? So it's absolutely happening. It absolutely works. Yeah.
Thank you. And thank you, Jacqueline. We do have 2 more questions in the Q&A, both from Paul Engelmeyer. And Paul's hoping you could discuss estuaries as a nursery and the fact that the majority of our estuaries, let's see, are on the CWA 303 D list. So having impaired water quality, which impacts juvenile species, and also your take on efforts to rebuild native oysters and oyster reefs.
Awesome. I think there's probably some other people on this call that can also speak to this. But it was oysters, and then the first part of that question was about the Clean Water Act and them being impaired, I think.
Yes. Yes, just mentioning this in the context that a lot of the estuaries are on the D list for Clean Water Act, and thus have water quality issues in addition to others.
Yeah. Some folks on this call will be better equipped to talk about the policy implications associated with the impairment status, but Like one of the other projects I've done associated with a lot of people on this call was looking at co-management of shellfish and eelgrass. And I think that's an active area of research. There's a lot of co-benefits between the two, but there can also be space conflicts. So I think moving towards improved co-management is something that at least the state of Oregon has put a lot of time and effort into. So that's very active, particularly if you add aquaculture shellfish into that scene. Yeah, I mean the water we know that water quality is impactful to seagrass, both from a water clarity and a eutrophication perspective. And I think that, like, if I were, the supreme ruler of the universe and I was trying to improve our coastal habitats, the first thing I would do is improve our water quality. That would be my magic wand wave, was to look at estuary and water quality. And unfortunately, I'm not, but but I think that's like an essential starting point that would be true for seagrass and so many other things, which goes hand in hand with the fisheries support. So yeah, I mean, I think I'll let somebody else talk more about the nursery habitat in their future talks. I know we have some queued up, but
Thank you, Melissa.
Yeah, thanks, Melissa. And I vote for you for Supreme Ruler of the Universe. I have one last question that it's a little bit off the cuff. So I just made a flight arrangement with Alaska Airlines, and I was prompted to offset my flight carbon impacts for a price. And I wanted to get your take on that.
yeah, and this is a fascinating subject. I guess I'm biased, but I have had projects funded by airlines before, like, who are looking, TAP Air Portugal, Air France, who like want to back up those claims, and they're looking for novel ways to do it, and that sometimes means seagrass or mangroves. And my personal take, and I respect the multitude of opinions associated with this, is that I just don't feel like I'm ever going to look back and think, gee whiz, I shouldn't have restored that mangrove forest. Like, I'll take any money anybody's going to give me to do that. That's fine. And I think that we're monetizing a single ecosystem function, carbon, and they're doing the restoration only for the carbon functions. But associated with that, if you monetized every ecosystem function, it's going to be way more. So even if, you're a little short on the carbon, or it's not that impactful from a carbon perspective, like if we were monetizing overarching resilience, the value would be way higher. And so I have no problem taking the money from Air France to restore a seagrass meadow. Like, I'll just take it. But like, I that said, we have to have rigorous methodologies and carbon markets with high integrity, like, so that we're not letting them off the hook. I wouldn't argue that we should like deregulate that industry, but I'm for it if it's high integrity, which we're moving towards. So I would not scrap the carbon market were it my choice.